All right, in this video lesson, we're going to be looking at how we can calculate and determine a chemical formula. Now, when we think of chemical formulas, we think of the traditional molecular formula that tells us the number and type of atoms that exist in the compound. And today we're going to look at a different type of chemical formula. This different type that only considers the ratio of atoms involved. But before we do that, I just want to remind you of the law of constant composition. So the law of constant composition tells us, or it states, that a compound contains elements in fixed proportions. What that means is that something like water, H2O, is always going to consist of 2 hydrogens and 1 oxygen atom. If you change the number of either of those atoms, you no longer have water. Okay, so before we continue, I just want to remind you that you need to hit pause and copy what you see here on your screen to put this lesson and this material into your notes so you have it to reference later. All right, so when we are talking about formulas, I kind of already mentioned that we're usually talking about or referring to the molecular formula, which you can see here up on my screen. So our molecular formula is a formula that indicates the actual number of atoms in one molecule of a compound. So the molecular formula of water is H2O. The molecular formula of hydrogen peroxide, I've shown you here, is H2O2. Okay. Now, our hydrogen peroxide is always composed of 2 hydrogens and 2 oxygens. Now, the other formula that we often don't really consider, it's called the empirical formula. And instead of giving the number and type of atoms in one molecule of the compound, it tells us the lowest ratio of atoms in the compound. So the molecular formula of hydrogen peroxide, shown in the green, is H2O2. But the empirical formula for hydrogen peroxide is HO. Even though a molecule of hydrogen peroxide has 2 hydrogens and 2 oxygens, actually a 1-to-1 ratio, 1 hydrogen and 1 oxygen. This empirical formula, it's based off of the percent composition of a compound. And we've talked already about how to calculate our percent composition. And it can be determined, and we can determine our empirical formula if we know the percent composition by mass, or if we're given mass of the compound and mole ratios, and using this thing called mole ratios. Okay, so we're going to dive right into an example. And in our example, it's asking us to determine the empirical formula for a compound whose percent composition is 21.6% sodium, 33.3% chlorine, and 45.1%, that should say oxygen. So we'll add that in here. There we go. All right. So what we want to do is we need to figure out the ratio of sodium to chlorine to oxygen by mass. We don't want it by percent. Okay. So what we're going to do is we're going to convert our percents into a mass. And because your percents add up to 100, if we assume 100 grams, then we can easily change our percents into mass information. So I'm going to assume 100 grams, and then I'm going to go through this process where I take my mass information and I convert it into moles. So I'm going to set up a chart, and what I'm going to do is I'm going to write element. I'm going to put mass here with my units. I'm going to put molar mass here in my units, grams per mole. I'm going to put moles here. I don't need a unit because the unit for mole is mole. I'm going to put ratio here. And then my last column, I'm going to write whole number ratio. Sometimes we don't even use this column. Now, the neat part about solving these problems for empirical formula is that if you just remember how to set up this table and then fill it all in, you're going to be able to solve the problem. So we're going to look from our givens. Our elements are sodium, and it was 21.6%. So that means if we have 100 grams of that, 21.6 grams is sodium. We also have chlorine, and 33% of that was chlorine. So our mass, is going to be 33.3. Fix that. Wow, my pen's not doing so hot right now. Okay, so I've taken my percents and I have turned them into masses. And this works because if I have 100 grams, then my percents, 21.6% becomes 21.6 grams. You're going to notice that I did not write units after all of the numbers, after all my mass numbers. It's because I have my unit in my table header. So they're in green. If I don't put my units with the table labels, then I have to write them in after every number. Okay. Our next column is molar mass. Now, this is something that you can super easily, you know how to do. You just have to get it from your periodic table. So I've just taken those from my periodic table. I have a mass number now. I have a mass given information and I have a molar mass. So I can easily calculate my number of moles. And just remember that number of moles is basically mass divided by molar mass equals. Right now, you guys should at this point be able to really quickly, without a conversion factor, calculate number of moles from mass and molar mass. So I want you to hit pause and I want you to copy, or I want you to calculate your number of moles for each of these three elements. And I want you to carry 4 decimal points. So just quickly check your work. You should have 0.9395 moles of sodium, 0.9393 moles of chlorine, and 2.819 moles of oxygen. Because our empirical formula is essentially a ratio of atoms, we are most concerned, we want to figure out what that ratio is. So we're going to use this mole information and we are going to determine the ratio of the atoms, the 3 elements compared to each other. So we're going to take our lowest number of moles, which is 0.9393, and we're going to divide the other numbers by this number. So I'm going to go, actually, I'm going to make a little note here first. I'm going to say, I'm going to divide by all right, if I take 0.9393 and divide it by itself, I get a 1. If I take 0.9395 and I divide it by 0.9393, I basically get a 1. And if I take 2.819 and divide it by 0.9393, I get a 3. Okay, so remember, I got these numbers by dividing the number of moles by the smallest number of moles. Our ratios at this point are whole numbers. So I don't have to do anything with this column. We'll look at what to do with this column later. So now I have these numbers 1, 1, and 3. This is the ratio that tells you the number of atoms in the compound. So if we look, this ratio tells you the number of each atom in the compound. So we have 1 sodium, 1 chlorine, and 3 oxygen atoms. So we can say that, therefore, the empirical formula is NaClO3. So make sure you have this copied. We're going to do another example. All right, our next example, we're going to, it's asking, what is the empirical formula of a compound with a percent composition of 38.16% carbon, 9.71% hydrogen, and 51.58% oxygen. Okay, so I'm just going to show you the solution here to save us a little bit of time. But I want you to notice I'm assuming 100 grams. I've set up my table. So I have my element, the mass, if I've assumed 100 grams. I have my molar masses I've taken from the periodic table. I have my number of moles, and I have ratios, and I write whole number ratio there in case I need it, so I don't forget what to do if I need it. So when I calculate my number of moles, my lowest number of moles is 3.177. So this is why I have that in a blue box. So I divide all the other numbers of moles by this number to get the ratio, and I get a 1:3:1 ratio. So that means my empirical formula is 1 carbon, 3 hydrogens, and 1 oxygen. So just make sure you have this copied. All right, now we're going to look at how to get molecular formula. To get our molecular formula, you have to have an empirical formula and molecular mass of the compound. So calculating the molecular formula is a lot less work than calculating our empirical formula. So we're going to keep going with the same example that we just finished. This is kind of like 2B here. So we want to determine the molecular formula of a compound if the empirical formula is CH3O and its molar mass is 93.12 grams per mole. The first step we want to do is we want to determine the molar mass of the empirical formula. So I'm going to use my periodic table, and I'm going to go 1 molar mass of 1 atom of carbon plus 3 times the molar mass of hydrogen plus the molar mass of 1 atom of oxygen. And I want you to note that I've included my units after all of my values from the periodic table. I do the math. My molar mass is 31.04 grams per mole. Now I'm going to take this number and determine my ratio of the molar mass of my compound to my molar mass of empirical formula. So it looks like this. My molar mass of my compound divided by my molar mass of my empirical formula. So I get my molar mass of my compound, my 93.12 grams per mole, and then the molar mass of my empirical formula, which I just calculated, 31.04 grams per mole, and I do the math, and I get a 3. This 3 is the ratio, is how many empirical formulas are in the molecular formula. So then we multiply the empirical formula by this ratio number that we just solved for. So molecular formula equals 3 times CH3O and then it's C3H9O3. Okay. Now, I'm going to get asked if you have to show your work. And yes, you do. Because if you make a mistake, you want me to be able to give you some process marks. So make sure you show me everything essentially that's in blue here for calculating our molar mass. So I just want you to make sure you have this copied, and I'm going to show you one more example because sometimes this whole number ratio I've talked about is going to come up. So let's take a look at our last example, okay? And I'm going to just breeze through it. I'm not going to do all the math with you. So I'm going to suggest that you watch and listen, and then you hit pause and you copy. So in this example, we want a molecular formula. We want to determine the molecular formula. Actually, I think we're just determining our empirical formula here. Oh, well, maybe we are. Of our compounds, we're going to go empirical. We want the empirical formula. It gives us a molar mass. We're not concerned about that right now, but it gives us some mass information. So it has 0.409 grams of carbon, 0.045 grams of hydrogen, and 0.546 grams of oxygen. Now, we don't have to assume 100 grams here because we already have our mass data in grams. So I've set up my table. I've gotten to the point where I have solved for my ratio. The problem is my ratio has a decimal, and I cannot have an empirical formula that has a decimal because I cannot have 0.3 of an atom. So I have to multiply my decimals by a number to turn them into a whole number. So if I take my 0.13 and I times it by 3, I can clear that up to become a 4. Punch it into your calculator. I promise it works. Because I'm multiplying my my 1.3 times 3, I have to multiply all of the numbers by 3. So they all get multiplied by 3, and I get a whole number ratio of 3 carbons, 4 hydrogens, and 3 oxygens. And that is what becomes your empirical formula. So sometimes when you multiply and get your mole ratio, you end up with decimals, and then you have to clear those up with multiplication. So here is a little help. Actually, make sure you got this copied down. All right, here is the little help. If you have something that's like a 0.1 or a 0.2, you can just round that down. So it can become like 1, or yeah, it's always got to be 1. If you have a 1.3, you can multiply it by 3. A 1.4 and a 1.5, they can get multiplied by 2. 1.6 can get multiplied by 3. 1.7 is rare. You probably won't get that, but you can multiply it by 3. And then 1.8, 1.9, you can round those to a 2. So basically, you have to multiply these decimals that you see are in the pink box. From 1.3 to 1.7, they have to be turned into a whole number through multiplication. But 1.1, 1.2, 0.8, and 0.9, they can just be rounded. If we wanted to continue this example and solve for molecular formula, we could just go through the steps that we've already learned how to do using our molar mass. Okay? But we will save that for later. We will do one of these in class together, and you will have a check-in or a quiz on it as well. So go ahead, go to our class website, and under determining formulas, there's worksheet 7 and worksheet 8 for you to be working on to practice determining our formulas.